Euler's number, and exponential functions. You're probably familiar with quadratic functions, which is x squared, x cubed, and ones like those. Well, there exists a function that is essentially the opposite of that, which is the exponential function. Instead of having x to the power of something, we have something to the power of x. So instead of f of x is equal to x to the power of 2, you would have f of x is equal to 2 to the power of x, which would look like this. You'll see that it never goes below the x-axis. This is because the function will always be above 0. The section to the left consists of very small values, but none of them are 0. This is because when you have a negative exponent, for example -1, you end up with a fraction with 1 as the numerator, which can never give a value of 0 or below. Now, you can have an exponential that gives you negative values, such as f of x is equal to -2 to the x, which would look like this. Looking at this, you can understand why it's shaped like this. It's a mirror image of the one I showed earlier. This is because we have some visible brackets here, which means that this is a negative image of the previous graph. Now, in theory, we can have -2 itself to the power of x, which is possible, but is hard to graph. If you have a negative base in the exponential, even powers are positive and odd powers are negative, which has to do with how negatives cancel. So what happens with fractional powers, once they're on whole numbers? If you try it yourself, you'll get some variation of math error, or maybe you won't. It depends on the power you used. If you used anything ending in 0.5, for example, that results in an error. The reason for this boils down to the fact that if you're using a fractional power, you're actually using roots as well as powers, and taking an even root of a negative number is impossible. This is why they aren't graphable. They don't produce continuous results. This covers most of what you need to know about exponential functions themselves. But what about the exponential function? Well, to explain that, first I need a new number. Introducing Euler's number. Okay, it looks like a letter, but it's actually a number. It's usually found on the calculator on the same button as pi, and above the times 10 button, and it comes out to 2 and a bit. It's an irrational number, like pi, which is probably why they're on the same button. The calculator will also have 2 variations of e, one with the box, which will be on a different button, and one without. Now that that's out of the way, here's the exponential function, e to the x. It looks exactly like every other exponential function, but there's something unique about it, and it has to do with the gradient. The gradient increases exponentially, because this is an exponential function, but we can find the gradient at any point through an easy calculation, e to the x. In terms of differentiation, this means that e to the x is its own derivative, but I'm not covering differentiation in this video. You may also have seen a capital E in some equation before, usually given to a power, like literally is. Don't let this confuse you. Capital E is a shorthand for times 10 to the power of, and is used in standard form and everything needs to be on the same line. This is why it doesn't appear on a lot of new calculators. They have the ability to accurately represent powers. This is also why you won't see E on an exam paper. They also have advanced enough software. But if you use the calculator on Google to work something out, it might give you an answer with E. So this is how you know how to use it. But why is E important? Well, E crops up in a lot of places, so it's important to know what it is and how to deal with it. As in lots of cases, it will require its own laws to deal with. But I'll be saving those cases for the videos on the functions themselves. And that's everything I have to say for exponentials. Although E makes an important appearance in dealing with logarithms, but those will have their own video, so look out for that.